Okay, so we're going to start talking about convergence of series some more, but we're not usually going to be able to find the sum of the series. It's very hard. We're going to look at some tests in the next couple of sections that help us determine if a series is convergent or not. But like I said, we're not going to be looking at the sequence of partial sums, and we're not really going to be looking at what the series converges to. The first one we're going to use is called the integral test. And it's very similar to what we were doing in section 7.8. You might want to go back and look at section 7.8 on improper integrals. For example, this is an example of an improper, I think this was a type 1 integral, where you have an infinite limit of integration. And the way we handle this type of improper integral, remember how you first of all write it as a definite integral, limit from 1 to t, and take the limit as t goes to infinity? Does that ring a bell? Then what you do is you compute the definite integral. You may have to use some technique of integration, and then after you compute the definite integral, you take the limit as t goes to infinity. And if that limit exists, then we say the improper integral converges. Well, we're going to use that to determine. We're going to use improper integrals to determine the convergence of infinite series. Okay. So this is a familiar improper integral. This is an example of this type of integral, 1 over x to the p. Maybe you recall that very popular one, the integral from 1 to infinity of 1 over x to the p, where p is a constant. As long as p is greater than 1, the integral converges, and if p is less than or equal to 1, it diverges. Anyway, that comes up a lot, so make sure you remember that one. All right, here we go. Let's take a look at, let's now compare this infinite series with this definite integral. There is, this improper integral I should say, there is a relationship between infinite series and improper integrals. If your delta x is 1, let's say that your delta x is 1 on each of these things, then the sum of the areas of these rectangles, the first area, since it's on the graph of 1 over x squared, and this is 1, would be, well, wouldn't the area of this rectangle be length times width? So it'd be 1 times 1 over 1 squared, which is 1. And the area of the second rectangle would be 1, which is the width, times the height, which would be 1 over 2 squared, or 1/4. So this has area 1/4. This third one has area 1 over 3 squared, which is 1/9, and so on. And it turns out what you end up with, the sum of the areas of these rectangles, okay, is actually, if you add them up forever, you get an infinite series 1 over n squared. So you could think of it like this. The sum of the areas of the rectangles is represented by this infinite series, 1 to infinity of 1 over n squared. And then the area under the curve, since you're integrating from 1, you would start actually here. The area under the integral from 1 to infinity would actually be the area starting at 1. So you'd have to add this first rectangle to it, and that has the area 1. But anyway, it's less than. Is that clear why the sum of the areas of the rectangles is less than the area under the curve? 1 plus the area under the curve, because you have all this error here. See how the rectangles is below the curve, or they're below the curve, so you're estimating the area under the curve. So that's one way you can say, since this integral converges, right? This is by the theorem above. This is convergent. This is a finite number, right? So what does that tell you? That tells you if this whole area under the curve is finite, and this infinite series is less than that, then it has to be finite too. So it shows us that it converges. That's where we're going. Let's try another one. Conversely, if you were to compare the infinite series 1 to infinity with the improper integral 1 to infinity 1 over x, the picture looks kind of like this. Remember, this is the graph of 1 over x here. So since the width is always 1, the area of this first rectangle would be 1 times the height, which would be 1 over 1. Since this is the graph of f of x equals 1 over x, so 1 over 1 times 1, which would be 1. That's the area of the first rectangle. The area of the second rectangle is the width times, which is 1, times the height, which is this distance, which would be 1 over 2. So if you think about it, if you add these areas up, you get 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. You get this infinite series, 1 to infinity of 1 over n. Now notice, because of the error here, the infinite series actually has more area than the area under the curve, right? So we just got through saying from section 7.8, this is an infinite number. This improper integral diverges. So this is an infinite. This is in infinity. Well, if this is more area than that, then this has to be infinite too. So that's what the integral test says basically. It says this. Suppose you have a positive and continuous decreasing function from 1 to infinity, and suppose the function agrees with the terms of the series, okay, at the integers. That's what this says. Then if the area under the curve is finite, if the improper integral converges, then so does the infinite series. And if the area under the curve is infinite, like the one we were looking at, then the infinite series has to be infinite too. So basically what we're saying here is you can determine the convergence of a series by looking at the improper integral. See? So that's why I'm saying you might want to go back to your 7.8 integration techniques. So it's when do we use this technique? We use this technique when the a sub n is easy to integrate. Okay, so we can determine if this series converges by looking at the improper integral. Now, by the way, I should mention, this is really important. It doesn't have to be from 1 to infinity. It could be from any number to infinity. The convergence does not depend on what happens in the first couple of terms of the series. So as long as the function is a continuous function on that interval, so we can apply the integral test. It doesn't have to be from 1 to infinity. It could be from any integer to infinity, as long as the function is positive, continuous, and decreasing. All right, so what are we going to do? We're going to look at this improper integral, and if this improper integral converges, then we're going to say this infinite series converges. And so we first write it as the limit as t goes to infinity from 5 to t. Now this is actually not that hard to compute, because if you let u equal the denominator, isn't du the numerator basically? So you get the limit as t goes to infinity of 1/3. I have a u substitution. I didn't switch the limits, so I'm just going to say x equals 5 to t. You could switch the limits if you want. But the integral becomes ln of absolute value of u, right? U is x cubed plus 1, so you get this. When you evaluate the limit, well, first you evaluate it from 5 to t. So when you plug in t, you get this. When you plug in 5, you get this. Now, what is the limit as t goes to infinity of this? This goes to infinity, right? So since the improper integral diverges, we say this series diverges as well. All right, let's take a look at another one here. This is the infinite series n equals 1 to infinity of 1 over the cube root of n to the 4th. Well, you might recognize this if you remember what we just talked about. This is actually 1 over x to the p, where p is 4/3. So you could use that fact. You don't have to actually do the integration. You could recognize this as a convergent integral 1 over x to the p, where p is bigger than 1. Since the integral converges by the integral test, that's what IT stands for. By the integral test, the infinite series converges. By the way, we don't know what the infinite series converges to exactly. Don't say it converges to some number. We do know it's finite. And again, if this were the integral from, say, 3 to infinity or 5 to infinity, this theorem still applies. Anyway, we call this a p-series. This theorem, or this fact for p-series is identical to the statement for improper integrals. A p-series like this form converges if p is bigger than 1, and it diverges if p is less than or equal to 1. In fact, if p equals 1, what do you have if p equals 1? Isn't that the divergent harmonic series, right? Okay, let's try another one. Determine whether this series converges or not. Well, this is actually, it's not a p-series, it's n over e to the n. So let's look at the improper integral x over e to the x from 1 to infinity. I think we need integration by parts, I believe. Integration by parts. So if you let u equal x and du equals, let u equal x, so du equals dx, and dv would be e to the x, dv is e to the x dx actually, and then v would equal negative e to the negative x, right? Anyway, if you use integration by parts, you get uv minus the integral of v du, v du, so you get minus a negative, that's why that's a positive, and you get e to the negative x dx. So when you integrate that, you get this. And remember, we first have to take the limit as t goes to infinity. That's kind of tricky. You plug in the t values, and you plug in 1 here. It's not obvious that that limit is 0, because you really have infinity over infinity. So so you have to show why this is 0. You'd apply L'Hopital's rule, and then you'd get 1 over the limit as t goes to infinity of 1 over e to the t, which is 0. So you have to show that. So anyway, everything both these limits equal 0, and this is actually negative 2 over e. So the final improper integral converges to 2 over e. That's not to say that the series converges to this, but since the improper integral is finite, it converges. We say the series converges. All right, let's do one more. Let's do one more. This one's kind of messy. I just thought I should do one of these so you can see how it works. But you might see homework problems like this. Find the values of p for which this series converges. Well, we're going to look at this improper integral, and we're going to look at cases. Okay, we're going to look at some cases here. If p equals 1, we know this integral diverges because well, we don't actually know that. We have to show that u equals ln of x. This is just u du, isn't it, basically? This is u du. So we get this. Limit as t goes to infinity from x equal 1 to t of u du, so you get this. And so the limit is clearly infinity, because as t goes to infinity, ln of x goes to infinity. I should look at this actually. Evaluate it between 1 and t, and then take the limit at the end. This term goes to infinity, so it diverges if p is 1. So let's get that out of the way. All right, now this one is a little more complicated, because if p does not equal 1, you use integration by parts. You're going to let u equal ln of x. U equal ln of x. Du is dx over x, and then dv would be x to the negative p dx, and v, if you integrate this, you get x to the negative p plus 1 over negative p plus 1, which is the same thing as x to the 1 minus p over 1 minus p. Anyway, so you get uv, which is this, minus the integral of v du. So we can integrate this now. We don't need to use integration by parts again to integrate that. The 1 over p factors out, and you just get this. You get x to the negative p plus 1 over negative p plus 1. But you already have a 1 minus p on the bottom, so negative p plus 1 is 1 minus p, so you pick up another factor of 1 minus p there. Anyway, so we're ready to evaluate this. It's kind of tricky. I mean, this is the messy part, I think. So I simplified this a little bit. I factored out the 1 over p squared from both of them, and I found a common denominator here. You can check me on that. Multiply back through. I guess I found a common denominator, then I factored out the 1 minus p quantity squared. So you get this. So when t goes to infinity, it depends on what p is. You get this. You get actually this. I plugged in t, and I plugged in 1. When you plug in 1, it simplifies because this term is 0. This becomes 1. This becomes 0. So you just get minus a negative 1, which is plus 1. Okay. Anyway, so now I have to take this limit as t goes to infinity. This is where I would consider, well, it turns out, I'll show you why in just a second. If p is greater than 1, it converges. If p is less than 1, it diverges to infinity. And you can see the reasoning right here. If p is greater than 1, you can apply L'Hopital's rule. It has the form infinity over infinity, and sure enough, you get 0. If p is less than 1, though, this has the form infinity times infinity. This is going to infinity, and so is that, so it diverges to infinity. So the final answer is the integral is going to converge if p is greater than 1. So therefore, the infinite series converges if p is greater than 1. Alrighty, we'll see you later. Bye bye.